All right, hello, and I am going to be now talking about concavity and the second derivative test. So in my previous video, I analyzed some of the theory and proofs behind um, the different definitions of concavity, right? But in this video, I'm actually going to talk about its applications analytically. All right, and to recall, right, the definition we're going to be using, at least like for, the first year calculus class, right? The definition of concavity we're going to use is we say a differentiable function f over a comma b is concave up if and only if f prime is increasing, or concave down if and only if f prime is decreasing. Now, this definition has certain geometric interpretations that I did prove, so if you do want to check it out, it's going to be linked. It's in another video. Right, so you have the secant line definition or interpretation. If f is concave up for any secant line drawn, the secant line is never below, and if f is concave down for any secant line drawn, the secant line is never above, right? So I'm going to show you the definition, right? First, we have f prime is increasing, right? That's what concave up means. But the secant line interpretation says that the secant lines are always above, right? And what are we going to do now, right? The tangent line interpretation, and that is that all the tangent lines lie below for a concave up function, and all the tangent lines lie above for concave down, right? And this is the tangent line interpretation for concave up. Notice all of the tangent lines are below the graph f, right? If you really zoom in, they all are below. All three of these interpretations, at least when expressed more rigorously, are equivalent, okay? But we have a test for concavity. Let f be twice differentiable over a comma b, all right? If f prime prime is increasing over a comma b, then f is concave up. As well, if f prime prime is decreasing over a comma b, then f is concave down. Okay, so how do we know this is true? I'm not going to prove it because it's actually rather trivial, but the reason why is because f prime prime is the derivative of f prime, and of course, if that's positive, right, by the derivative of the pi monotonicity theorem on f prime is increasing, meaning f prime is therefore concave up. Now, however, on the other hand, the same thing applies for concave down. I'm not going to spend too much time on the proofs, except for a few things. So first, we're going to define a point of inflection, right? Or an inflection point. We say x naught is an inflection point of f if and only if x naught is an interior point of the domain. Locally at x naught, f has to change concavity, or that's equivalent to saying f prime changes monotonicity, or f double prime changes sign. Okay, we've established those are all equivalent, right? And the other one is that what was I gonna that the other part has to do with f prime being differentiable. This one, or sorry, f being differentiable, this one is a bit more if because iffy because this definition requires the tangent line to f at x not to exist. Some books, right? Some books will not require this. Okay, but right, for our sake, we're going to say the tangent line has to exist. We don't want an abrupt change in concavity. Right? We want it to be smooth. So let's look at some points of inflection. X naught here, point of inflection, changes concavity. To the left, it's concave up, to the right, concave down. X naught, point of inflection. To the left, it's concave down, to the right, it's concave up. Here, X naught is a point of inflection, right? To the left, concave up, to the right, concave down. And even though, right, it's not differentiable technically, it has a vertical tangent, which satisfies their definition. It's not like sudden. Now, if we want to find points of inflection, right, we want f prime to change monotonicity at x naught, right? But that means x naught is a local extremum, but so by the zero derivative of a local extremum theorem, either f prime prime is zero or it's not real, meaning we're looking for critical numbers, not of f prime. We're looking for critical numbers of f prime. Here's an example. Determine points of inflection of f of x is equal to x to the fourth minus 4x cubed. I'll make it quick. You take the derivative, f prime, and then you take the second derivative, f prime prime. So that's 12x squared minus 24x is equal to 0. We want to find word 0. It's differentiable everywhere, so we want to find word 0, right? And hopefully you know how to do algebra and determine that it has zeros at 0 and 2. So we're going to draw this table, right? f and f prime. In this case, we only need f and f prime. Okay, and we're going to write our critical numbers for f prime here, and we're going to determine the sign, right? And either you can use inequalities, right, or you could use test values like we did with the first derivative test. Either way, as long as you find the sign of f double prime, and note that the sign of f double prime determines concavity. So since f double prime is positive here, negative here, and positive here, we have that f has points of inflection at x equals 0 and x equals 2 because f prime prime changes sign there. And if they ask us to determine concavity, we also have that here. Now we have a theorem, and this one I will prove. The second derivative test. This is for a local extremum, and it is extremely useful. The first derivative test can take slightly long. If you're on an MCQ, if you can, try to apply the second derivative test. Now, the second derivative test cannot be used universally. While the first derivative test can be used, right, everywhere, for any function, the second derivative test has an extra condition, right? And that is that the second derivative is not 0 at a point. But we'll talk about that in a bit. So it says that if the derivative at x naught is 0, okay, right, we have a candidate for a local extremum, and f double prime is positive, then f has a local minimum, okay? F double prime is positive means f is concave up, so we're gonna have somewhere this, and where f prime is 0, right, we have, notice, a local minimum, okay? So hopefully that's a bit more clear. But if f prime is 0, right, candidate for local extremum, and f prime prime is negative, then f has a local maximum. And we're gonna prove one, and I guess we're gonna you can do the second one, I guess, as an exercise. I'm only gonna prove the first one. Second one's identical. F double prime is the derivative of f prime, which is the following limit, right? And we said f prime of x naught is 0, which is this limit, right? But of course, if the limit of a number, right, is positive, right, which we said is true, we said f double prime is positive, then locally in some neighborhood, at least the function itself has to be positive, right? And this is f prime, right, so don't get confused. The function has to be positive in some interval. There's no way that the limit is positive and yet the function is negative for any interval containing x naught or surrounding x naught, not containing x naught. So x minus x naught is less than 0, so f prime is negative, meaning f is decreasing at x naught minus to the left of x naught. And to the right of x naught, x minus x naught is positive. So of course f prime also has to be positive. So it's increasing. So by the first derivative test, we've already proved, right, f prime changes sign, right? So f has the local minimum at x equals x naught. And this concludes our proof, okay? Now we're going to do some examples of applying the second derivative test. So how are we going to do that, okay? So in order to find, we're going to use the second derivative test wherever we can, right? And here is, I think, a good example, right? So um, we're going to do the following problem as an exercise, okay? F of x is equal to x to the fourth minus 4x cubed plus 2. Hopefully, you should know kind of, how to apply the first derivative test. But first, we're going to apply the second derivative test. We're going to find f prime of x, right? We're going to say that that's 4x cubed minus 12x squared. And we're going to find where it's 0, okay? So it is 0 if and only if we're going to factor out a 4x squared. We're going to get x minus 3, just minus 3, right? So we have so we have critical numbers, right? What critical numbers do we have? So we're looking for critical numbers of f, and that's equal to 0. All right, so we have critical numbers x equals 0 and 3. Okay, so why not draw our little table? Okay, so actually we want to find, I don't think a table is necessary, but you should get a table. But if we're only looking for relative extremum, we just want to test at the critical numbers. So these critical numbers happen to be where the derivative is zero, right? Not just critical numbers specifically. F prime is zero at those points. So we can try to apply second derivative test. So notice f prime prime of x is equal to, what is it equal to? 12x squared minus 24x. All right. And hopefully, maybe if you want to factor it, I think it makes it a bit nicer to work with, x minus 2. You should notice that if we want to figure out the sign f prime prime of 0, that is just, if you want to test it out, f prime prime of 0 is 0, okay? And f prime prime of 3 is, if you want to verify, it's positive. Can we apply the second derivative test to the critical number 0? The answer is no, we cannot, because the second derivative is 0. Instead, we're going to have to apply the first derivative test. And now is where we get out our table. Now, we did confirm, though, that 3 is a local minimum, sorry, right? Because f double prime is positive, right? Meaning it's concave up, so it has a minimum. So we did confirm that at, I think, x equals 3, we have a minimum. But what we didn't confirm, however, is at x equals 0. So that's what we're going to show, okay? But of course, since 3 is a critical number, we do still have to include it in our table, but we're not going to consider it, okay? Really, we don't have to, but we're not going to consider it, but for simplicity, of course. So this is f prime, okay? Notice x squared is always positive, 4x squared is always positive. So we're only looking at x minus 3. That alone determines the entire sign, okay? So to the left of 3, it's negative. Oh, sorry, that's f prime. To the left of 3, it's negative, right? But to the right of 3, it's positive. So decreasing here, increasing here, okay? What does this mean, okay? So notice that at 0, there is no change in monotonicity, okay? We do not have any change in monotonicity. So essentially what we're going to, what I want to show is that we do not have any max or min at 0, but instead what we do have is that f has a local min at x equals 3 by the second derivative test, because why? Well, we want to justify because f prime of 3 is 0 and f double prime of 3 is positive. Look how simple that is. We don't need a table. We don't need anything. On MCQs, it's rapid, it's fast, and we have proven that it's a local min. However, in the case where we cannot apply it, we can use the first derivative test as normal. Of course, you could also use the first derivative test to justify that it's a local min because f prime changes sign from negative to positive at x equals 3. Right? That's another justification using the first derivative test. So we've shown that they're the same, right? And maybe you want to verify that graphically, right? What would that graphically look like? Well, believe it or not, it's actually not that hard, but um, basically at 0, we have the first derivative is 0, but the second derivative is 0. I'm not going to show this, but if you wanted to show concavity, you would indeed figure out that the second derivative being 0, um, as well as it is, there's a change in concavity. It's an inflection point, right? So that's why f prime is 0, right? Not that so it's a point, it's an inflection point, right? So of course, because it is an inflection point, we cannot say that it's a local max or min, right? Even if the derivative is 0. On the other hand, since it's an inflection point, we don't have concavity at that point. If it was positive or negative, we would have concavity to determine whether f prime, sorry, f has a max or min. And hopefully that makes sense. All the problems are like this. Find f prime, find the critical numbers of f prime. Make sure that that makes the f prime 0. So not really critical numbers, but what numbers make f prime 0? If you have critical numbers outside of those that make f prime 0, presumably what you're gonna have to do is apply the first derivative test. Um, And of course, then you could just plug in the value and determine if it's concave up or concave down, and from there determine whether it's a max or min. Hopefully this helped, and if you need extra help, I may upload a video doing some practice problems, but this is just the main theorems and concepts behind it.